Hey Ramakrishna, good evening. Hello, you are on the mute.
Yeah, good evening.
Last time I think you are not there.
Yes, I was busy, so I couldn't attend.
Welcome. Vishwanathan? Yeah, good evening. Good evening, Atul. Vishwanathan, Atul, you are on the mute.
Good evening.
Yeah. So you are also, I think 1 or 2 sessions you are also not there, no?
Yeah, I joined initial 2 sessions, I think. After that, I had to move to site actually, so I couldn't join. Today, I was back at home, so I thought I was here in Qatar. Depends which client.
Material engineering, so for you also they used to send on site and that one?
No, there are many things like there are discussions on engineering activities. Then after that, during the construction phase, any requirement for the corrosion monitoring installation, request from them.
So that meetings and that one you have to go there and you have to attend, right? Saudi or
Yeah, based on request, like depends.
and the HS this safety and that one they used to go site and that one to check that seal and that hazop and that one on that time they used to go, but means material also is required to go there, means that site and then you have to attend the meeting. So, good. So it will be you will more in the practical rather than the sitting in the office and doing the job. It's good to going there and
Yeah, definitely that is good.
yeah. So what the issue you found there in the recent site visit?
Sorry, sir.
What the issue you found in the recent visit or anything you want to like to share? Or?
No, this was last time I went to have a engineering deliverable meeting. Like basically, we have developed a metal selection report and corrosion management program. So client want to have a discussion on that. Like he want to see how justification of metal selection and justification of the monitoring parameters we have recommended. So it's an engineering meeting basically. I didn't go to site, but basically the client premises.
Okay. So material selection and monitoring. So monitoring you used to put some what camera or sensor something. What you'll do?
It's basically corrosion coupons are there, corrosion probes are there. Then you have non-intrusive monitoring. Like you have a sensor outside, and then you have ultrasonic thickness gauging, which is non-intrusive. Just you will attach the equipment outside, and it will keep on giving you the thickness reading. So there are various monitoring techniques are there. Intrusive, which will enter the system and then give you the signal for corrosion rate. And there are some systems where it will give you external sensors.
Okay. But this corrosion and that one, it's not happen in 1 day or 2 days. It takes years to happen and to get reduce that thickness, and maybe it takes months or years to reduce. Maybe from 20 mm to 19 mm, it takes several months. No. So it you have to verify that one on daily basis or on yearly or monthly basis. How it will be?
No, basically I think I have some that.
Yeah, sure. It's okay, no? All of you. Yeah, it's good, knowledgeable. We can.
Knowledgeable, yes.
So I think you can see the presentation. I think. Hello.
Yeah.
Yes, we can see.
Yeah. So basically, we need corrosion monitoring. So generally, to proactive and predictive ways to avoid corrosion failures. So this is what I was telling is one of the intrusive method wherein there is a coupon that will go inside, and then it will interact with the process fluid, and then there will be a corrosion. Okay, from the coupon we will get signal, and then we will get to know the corrosion rate. If it is a coupon, then this coupon will undergo weight loss, and we will measure a weight loss every 3 years, and then every 3 months, and then we'll get to know the corrosion rate over 3 months. So with that, we can find the millimeter of corrosion per year. How much millimeter lost per year? Okay. But if it is a sensor or like a probe, then we can get the reading instantly. So we have electrical resistant probe and a linear polarization resistant probe. So those are all probe. If it is coupon, we have coupon. Okay. So basically, to to predict the corrosion. It's in simple words. So it's a 100-slide presentation. I'll make it very simple and okay. So corrosion monitoring, changes in corrosivity is expected, prolonged deviation is unacceptable. So for these reasons, where the changes in corrosivity is expected, where you have different operating conditions and where your corrosivity might change and then you have to predict it or you have to foresee it. And then when you operate in a prolonged non-steady state or transient conditions, then the corrosion rate will be higher than the expected. Okay. So these two events we want to see the corrosivity so that we don't end up in failure.
Okay.
So then we have two types of monitoring. Direct technique. One is intrusive. Intrusive means what I have shown in the first slide. It will go and interact in the system. Non-intrusive means it will be in the outside.
Okay.
And online means anything which is at the instance. And offline means anything which is taken to the sampling, like sampling, taking the process fluid sample and then taking it to the laboratory and then finding the readings. So those are all called offline. But anything you check directly in the system is called online. And anything which interacts with the system directly is called intrusive. Anything which does not interact but gives you the reading is called non-intrusive. Okay. So then we have intrusive and non-intrusive. So we have physical coupons, electrical resistant coupon, internal visual inspection. Okay. And there are electrochemical methods like linear polarization resistance. These are all various techniques we have. Okay. And then non-intrusive is nothing but you can have a physical UT measurement at a local thickness location and then you can find the difference in thickness. Okay. Over a period of time. So if I have a thickness measurement today and then after 6 months if I measure the thickness, I will get to know the wall loss. Like that we have other non-destructive technique methods for monitoring. Okay. And then we have a lot of sampling in the laboratory, like we can sample for pH, conductivity, dissolved oxygen, pressure, temperature, dew point, water chemistry, alkalinity. Okay, so we have a lot of things. When you take a sample from there, you can measure a lot of things in the lab and then you can find out the corrosivity as well. So generally what we use is corrosion coupon, electrical resistance probe, linear polarization resistance probe, especially in oil and gas industry, hydrogen probe and bioprobe. And when the sand is coming from the well, we use acoustic sand detectors in case of sand production. So these are all the common techniques we use in the oil and gas industry. So we have corrosion coupons, variety of coupons. So you will insert the coupon here. This coupon will interact in the system and then it will undergo corrosion. Once it undergoes corrosion, there will be a weight loss. And based on the weight loss, we can convert that into a corrosion rate. So we have standard for that, corrosion coupon, NACE SP0775. Okay. So the technique is very simple. Expose a coupon to process environment for a given duration and then removing the specimen to measure the weight loss. Okay. So the weight loss is taking place over the period of exposure is expressed as corrosion rate, either milli inches per year or millimeter per year. So you have a flat coupon, you have this sort of coupon. There are various configurations are there in the form of coupons. Generally we use the flat coupons, or even when required we will use the disc or flush type coupon. Okay, if you want to simulate a weld, this HIZ zone you want to simulate, you have a coupon like this. Okay, if you want to use a stressed coupon, you can use like this. If you want to have a scale or biofilm, if you have a bacteria in the water, or if your water tendency, scaling tendency is high, you can use this. In this case, you will have a weight gain instead of weight loss. Okay. In scale coupon and most likely in biocide coupon will catch the microbes. Then you will measure the number of colony forming units per ml. But in case of scale coupon, it will have weight gain. So it will form scale, and the increase in weight gain determines the scaling tendency. You have various type of coupon and coupon holder. You have scale coupon wherein your scale will go and fit in different hole size. Okay. You have stressed coupon. You have welded coupon. If you see this flush disc coupon, what I have shown in the first slide, this coupon. So this coupon is fitted like this.
Okay.
The flush disc coupon is fitted like this. Okay.
Where is that flush here?
It will fit like this in the pipe. It will fit like this.
Okay.
It will be exposed to the process fluid which is coming here.
Okay.
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 And there are normal strip coupons which I showed. There are strip coupons are also there. This is the flush coupon, strip coupon. Then you have a disc coupon, disc loaded into multiple levels if the pipe size is higher. And you have a ladder type coupon. Suppose your pipe is having half is flowing with oil or water, and half is flowing with gas. Then these type of coupons will help you. Okay. Now the half of the pipe you will have water and oil, half of the pipe you have gas. So this will predict the gas corrosion rate and the corrosion rate due to the gases flowing at the top of the pipe. Whereas this will predict the corrosion rate due to the water or oil in the pipe, and this will predict the half will predict the water and oil, half will predict the gas, the combined scenario.
Okay.
So sometimes we use this also, ladder type coupon we call. Ladder type coupon. We also use this. This comes mainly when there is a pipe size is higher, like 30 inch or 32 inch, and then you have a two-phase flow, like gas and oil flowing in a separated fashion, like in a way that the oil is flowing at the bottom and gas is flowing at the top. Typical to a stratified wavy flow.
Okay.
So corrosion coupon. So you have how you will determine that how many days I have to expose. Minimum length of exposure for corrosion coupon is 3 months. Okay. But you can find out, like if you expect the system to corrode in a particular corrosion rate, then you can divide it 50 by expected corrosion rate. That will give you the number of days you need to expose. Okay, this is just a general calculation as per ASTM G311. If you expect that your system will give a corrosivity, if your system is corrosivity is like 0.1 mm per year, then 50 divided by 0.1 will be your exposure days. Okay. So if it is 50 divided by 0.05 means 42 days. 50 divided by 0.1 means 21 days. Okay. So you have this corrosion coupon NA standard, preparation, installation, analysis, interpretation of corrosion coupons in oil field operations. Okay. So the general, how we get the corrosion rate? So based on the weight loss, W into 365 into 1000. So this is given in SP 0775. W into 365 into 1000 divided by ATD. A is the initial exposed surface area of coupon. T is the exposure time days, like 21 days, 42 days, like that. D is the density of coupon. That basically we use carbon steel, so 7.85 gram per centimeter cube. So basically, if you get the reading like this, then if you put all the values together, then you will get the corrosion rate. Okay. So then if you have a localized corrosion, which is called pitting, the formula is different. Depth of the deepest pit into 365 divided by exposure time days. So once you get the reading, you can find it. Like if you have a corrosion rate which is less than 0.025 mm per year, that corrosion rate is considered to be, that corrosivity is considered to be low. Okay, if you have 0.025 to 0.12, that corrosivity is considered to be moderate. This is general corrosion rate, please note. If you have 0.13 to 0.25, then that is considered to be very high. If you have greater than 0.25, that is considered to be very severe. And pitting rate, if you consider less than 0.13 is low, 0.13 to 0.20 moderate, 0.21 pitting means localized area. Like it is not a general corrosion rate, but it's in a very localized region.
Okay.
So corrosion coupon, the limitation is require long exposure duration. So provide average corrosion rate and not instant corrosion rate. Suppose you don't have a corrosion rate for 30 days, and then you have a very high corrosion rate for 30 days. And another next 30 days, you don't have much corrosion rate, but you have some corrosion rate. If you take a coupon, you don't know this thing that first month there is no corrosion, second month there is a heavy corrosion, and third month you have light corrosion. This one you don't know because it gives the average weight loss over 90 days. So you never know that when the high corrosion happened, when low corrosion happened. That is one of the disadvantages of corrosion coupon. Nevertheless, we use always corrosion coupon to complement the corrosion probe. Used coupon cannot be reused. Coupon need to be removed and cleaned for analysis. So these are all some limitations. Then we have electrical resistance probe. This is like a electrical corrosion coupon. We call it as electrical corrosion coupon. Like basically this is all equivalent to a corrosion coupon, but it gives the instant readings. Okay. So if it is operating on the principle of resistance technique. So you have a element or a probe which is exposed to the process fluid. Okay. Now there will be a probe which is exposed. Now we know that in electrical this thing R is equal to rho L by A. Okay. Resistance or resistivity is equal to rho into L by A. L is the element length, A is the cross sectional area. So this one. So resistance is equivalent to the resistance or resistivity of this equivalent to this equation. Now when the probe is undergoing corrosion, the area will get reduced. And the area gets reduced means your resistivity or resistance will increase. Okay? So based on that, if your resistance increases, that means your area is getting more and more reduced. That means the system is undergoing high corrosion. Okay? If your area is reduced too much, then the resistance increases, and once the system resistance increases, which is measured by the instrumentation, it indicates that you are undergoing very heavy corrosion or high corrosion. Okay. So this is the principle of operation. So I think there are various type of electrical resistance technique probes are there. Like you can use the same like a flash coupon, disc coupon like that. Here also there are wire loop probe, cylindrical probe, tube loop probe, strip loop probe. There are various forms of probes.
So this use immediately means
that.
on that time only you will find how much corrosion is happened, right?
Sorry, sir.
You said that it is immediately you will come to know this what is the corrosion rate, right, by using these probes.
Yeah.
So immediately when you attach this one, it says that this much corrosion happen in so many days, like that. How it is?
Yeah, I'll show you. I think I have a slide for that. I think.
Okay.
So the thing is that there are two types of probe in this also. Okay. If your system corrosivity is very high, then the normal probe will be very useful. Normal probe means like this sort of probe, this probe, where is the system corrosivity is high, then you will have lot of corrosion damage, and then the resistance will increase. So easily you can detect. But if the system corrosivity is very low, the system is not corrosive, very corrosive, then the area reduction due to corrosion is less. So the corrosion sensitivity, the sensitivity of detecting the corrosion rate becomes a problem. So if there is any system, there is always a problem. If the system is less corrosive, then you will not find if there is a small corrosion, you will not find it immediately. So you need to go for high sensitivity probe. We call it as high sensitivity. That means you will have a small thin tube or thin wire. Even if there is a small reduction in area or small corrosion, the resistance increases. Okay. So if you go for a large area, then you need to have a substantial amount of reduction in area due to corrosion. Then you will get indication. But if you have a small tube like this, even if a small corrosion, then the resistance increases, and then you get to know. So this is called high sensitivity probe. This is called normal sensitivity probe. Okay. Now how it will show, I will show you. Why I am saying is that basically in some applications where there is less corrosivity, we will go for high sensitivity probe. Where the system is having low corrosivity, then we will go for this one. When the system is having high corrosivity, we will go for normal this thing. When the system is having low corrosivity, low anticipated corrosion rate, then we will go for high sensitivity. Okay. So this is the way it is. Like we will launch the probe here. Okay. There are three types of probe. One is fixed. You can see that there is a wire loop here, and then there is a retractable probe, and then there is a retrievable probe. Okay. This is a temporary. Wherever there is a drain nozzle 2-inch, you can install this retractable probe. But you can install up to, I think, 300 pound pressure rating. After that, this is not possible. This is going, fixed probe will go up to 10,000 pound rating or 15,000 pound rating system. You can install this fixed probe. But the disadvantage is that you can remove only after the shutdown. You cannot remove in operation. Retrievable probe up to 1,500 pound rating service we can do. and you can retrieve during the service. Okay. So this is what I was telling. Like probe life, you see. Basically, the thing is that if you have a strip and all, okay, then it will have the thickness is 10 mils, 10 milli inches. Okay. Whereas in the tube loop, the thickness is 4 milli inches. That means it's very thin. This is high sensitivity. Whereas this cylindrical, spiral and the surface strip and all is low sensitivity. But on the contrary, you will get high sensitivity probe means you will get the corrosion rate instantly, but the life is half. Like if you have 4 milli inches thickness, when it becomes 2 milli inches, you cannot further use it. It will corrode, it will after 2 milli inches, it will corrode faster and then the probe will have discontinuity. The probe will corrode and then the circuit will break. The probe will corrode and then the circuit will break. And then it will not pass signal. So basically when the probe size becomes from 4 mil to 2 mils, you have to change the probe. Whereas in the surface strip like 10 mils or something like that, you have a longer life. Okay.
Okay.
So this is the one thing. High resistance probe, we can use high sensitivity probe, but only thing is that we have to change it very frequently. Like once in 2 months or once in 1 month. But if you have a surface strip, you can change it like once in 4 months, once in 3 months, something like that. But as I said, it depends upon the system corrosivity. We have to select accordingly and how much reading we want. So the calculation is very simple. You have a total metal loss and there is a linearized signal given by this probe. Okay. The signal system, the probe will give a linearized signal. Then you have a probe life P. Okay. Then you are divided by 1000. So basically, if you have a probe life, you know that probe life. Probe life is this value. Then you have a signal between initially there will be a signal when you install, and then finally there will be a signal when you uninstall. So you have to minus that signal 2 minus signal 1 into 365 divided by 1000. So the corrosion rate, this is metal loss, this is corrosion rate. Okay, there are two equations. So we can calculate. So this is the response. This is what I was, your question, sir. Okay.
Yeah.
Now if you see this, actually, response time with respect to corrosion rate. If you have a 35 milli inches thick probe, okay, the response time for a corrosion rate, similar corrosion rate, like let us have a corrosion rate here, or let us have a corrosion rate here. This is the way. Okay. This is response time hour. When you have, your system is having a corrosion rate of 1 mils per year, let's say 1 mils per year or 2 mils per year. Your system is having a corrosion rate of 2 mils per year. If you have a 35 mil thick probe, then a system with 2 mils per year corrosion rate, that probe will give you signal after 1000 hours. Okay. Whereas as linear, this one is a very high sensitivity probe, this one and this one. If it have 2 mils, then this probe will give you 2 mils means it will give you in 0.4 hour. Okay, the response time. It will give you signal in 0.4 hour if you install a high sensitivity probe. Okay. If you install a thick probe, then it will give response for 2 mils corrosion rate. It will give response in 1000 hours. Okay.
So thick one
So
will be
basically
take
that's the
more time.
difference. So
Thick one is
so for a system which is having low corrosivity, you need to use a high sensitivity probe. For system with a high corrosivity, you can use this one. So if your system with a high corrosivity, you see if it is like 100 mils per year, okay, this will not work at all because this will corrode faster and this will not work at all. But this one will give you reading with 20 hours. Okay. Whereas this one will not work at all because this will corrode and totally the probe will get corroded totally. Okay. So for high corrosivity system, you have to use a thicker probe, whereas for low corrosivity system, you have to use a high sensitivity probe or a high sensitivity resistance probe. Hope I answered your question, or
Yeah, I got. When we want to know in the shorter period, then we have to use high sensitive one, and
exactly, sir. Exactly. Fantastic. That's the point.
Okay, sir.
Then we will go for the third probe, which is linear polarization resistant probe. So basically here you have, principle of, there is a electrochemical technique and there is a principle over there. So this can be used only in the aqua system, like in the water systems. Okay. Okay. So I don't want to take the electrochemical principle, which is more into corrosion science. That will be boring for you.
Okay.
So basically what they do is like this gives instant corrosion rate. In both the cases, like corrosion coupon and electrical resistance probe, you need to calculate the corrosion rate with the readings. Okay. Whereas in terms of linear polarization resistance technique, it will give you instant corrosion rate. Like this is one technique where you get the corrosion rate on the screen, per year or mils per year.
Okay.
So now I can show you a graph where I have installed in a system the probe installed, okay, and there is a corrosive fluid is going in that, and then I am putting a corrosion inhibitor. I am introducing a corrosion inhibitor. Okay. Orange is one type of corrosion inhibitor, and green is another. Blue is another type of corrosion inhibitor. Once I start introducing that corrosion inhibitor, you see the corrosion inhibitor starts functioning, and then after some time, the corrosion rate drops. Okay. For the non-aged corrosion inhibitor, it takes 4 hours, and for the aged corrosion rate, means it takes 2 hours, 2.5 hours. Okay, we will not regard what is non-aged or aged, that is a different issue. But what I'm saying is, you can see that directly you can see the corrosion rate mils per year. This is the advantage of LPR technique. LPR technique will give you the direct corrosion rate. There is no calculation involved. You don't need to do any calculation. Only problem is, the LPR can be used only when there is aqua system. When water system is present, then only you can use linear polarization resistant technique. The problem is because the principle of LCR is based on electrochemical technique. Electrochemical means you need an electrolyte, water. Aqueous conductive electrolyte you need. Once you have the electrolyte, then this principle will be applicable. Electrochemistry principle is actually applicable. Once you apply the electrochemistry principle, then you will get this thing. But the electrical resistance probe, the previous one we discussed, can be applied in any this one. It has nothing to do with the water or oil or this thing. It is only purely based on corrosivity. If you have a corrosive this thing, then the resistance will drop. Then resistance will increase due to the probe corrosion, and then you can use the electrical resistance probe. But in LPR probe, if it is an aqua system, you can use this one. But this is very fantastic. Like you don't need to calculate anything. It will give you the direct corrosion rate. And instantaneous also. Okay. The thing is that
it requires fluid.
LPR is used in aqua system. Basically, we will use it in cooling water services or system with containing some water. Even that water also should be conductive. In case of DM water, we cannot use LPR because DM is non-conductive. Okay. So we have a lot of electrode configuration like 2 layer, 3 layer, 3 electrode, 2 electrode. Okay. So the electrode position is like if you have a flow, you can place the electrode like this and not like this. So the electrode will have a phased in a conductive solution, and there will be like one electrode will act as an anode and another electrode will act as a cathode. So benefits is very fast, data within minutes, well suited for water system, can be used to monitor corrosion inhibitor performance. Okay. And the thing is that limitation is need conductive medium, not suitable for most oil and gas process, because oil and gas will have more of oil or gas and water is less sometimes. So basically we cannot use in oil systems or gas systems. Assumes one anodic and one cathodic reaction far removed from the reversible potential. This is because electrochemical principle. Okay. So then we have hydrogen probes. I think this is sometimes used when there is a need to detect the hydrogen evolution due to corrosion reaction. When due to some corrosion reaction, there is a hydrogen charging into the metal. Like last time we discussed about the stress sulfide stress cracking, wherein the hydrogen is charged into the metal, and then the hydrogen will come out of the metal. So that hydrogen we can capture in the hydrogen monitoring, and then based on that we can determine the corrosion rate or the cracking tendency. So this is the probe. The probe, there is a corrosive fluid here, and then due to this corrosive reaction, the hydrogen gets charged into the metal steel. Okay, and then it will come out of the material. Now you fix the probe here and then catch the hydrogen that is coming out of the metal, And then based on that, we can extrapolate that into a corrosion rate or cracking tendency. Okay. So this is the function of hydrogen monitoring. There are various type of probes. Okay, you will have a sealed cavity probe, and then you have a vacuum probe. So mostly this probe is used. Okay. This probe is mostly used. Okay. Because it is non-intrusive. Rest are all intrusive. Intrusive means go into the system. Okay. So in hydrogen monitoring, what we do is there is a flux thickness ratio. Okay. That's the one we are finding. And then that is extrapolated to corrosion rate. These are all graphs provided by the probe vendors. They have some experiments done, and they have this graph. So they have this flux thickness ratio calculated, and then they have the corrosion rate correlation. I'll tell you what is flux thickness ratio briefly, because this principle is basically on the fixed first law of diffusion. So flux is equal to flux J is equal to F into C into A, F into C divided by A. Okay, A is the area and F is so this formula is used. C is the hydrogen concentration. Okay, and then hydrogen captured from a well defined area. So this area is the A. Okay, and this C is the hydrogen concentration, and F is the flow of total amount of air that is taken from this area. Okay. J is the flux. Okay. Now this flux is calculated, and then it is with respect to a particular thickness of the pipe. Okay. So that is called flux thickness ratio. Okay. So the flux thickness ratio is correlated to corrosion rate, and then it is also correlated to cracking tendency. Okay. Now for wet H2S damage, if it is 1 bar, 10 bar, 100 bar, 1000 bar, then there is a chart is there. Okay. Is the steel more than 13 mm, 18 mm thickness? How is the quality? It is source service? Yes. Then the total activity what we measured is 100 to 10,000 bar. Then 1. Okay. 0 is no hydrogen damage risk. 3 is very high. 1 means small risk of crack initiation, some risk of crack propagation, especially is steel known to be susceptible. Okay, this is less risk, moderate risk, high risk. 0 means no risk. Okay. So based on that, the flux thickness ratio converts to a hydrogen partial pressure or activity, and the hydrogen activity is converted to whether it is risk is no risk, low risk is medium risk or high risk. Okay, these are all given by the vendors. Then when the sand is produced from the well, there will be acoustic sand detector. Okay. So that the sand is coming along with the fluid. Okay. Then you have to detect the how much sand is coming, and then the sand will hit the wall and then start erosion corrosion. So you need to find that also. Okay. So you will attach the sand detector to the pipe wall only like this, like from horizontal to vertical elbow or vertical to horizontal elbow, depending upon the elbows what you have in your isometric. After horizontal to vertical or vertical to horizontal, that after the elbow you will attach the acoustic sand detector. The impacting particle will impact the wall of this, and based on the number of impact, this detector will detect, and then it will filter out the noise, and then will give you a sand loading. Okay, sand milligram per minute or something like that, like loading. How many sand of grams per minute it is loading? Yeah. So that much it will give.
But all sand will not hit that one, no? Some sands may go below also.
Yeah, that is correct, sir. Very good, sir. That one is correct. What I am saying is, here, the sand particle detection limit in liquid is greater than 25 microns. In gas is 15 to 25 microns, depending upon flow rate and viscosity. So you are right. Actually, the system has some limitation or some, how to say, some minimum particle diameter that it can detect. Okay. And the corrosivity is greater only after 70 microns. Till 70 micron it will get loaded, but it will not be corrosive or erosive basically. Okay. So that's how it is. Then this is one of the sand data actually. Suppose this gives you the metal loss, that yellow.
Mm.
Okay. Acoustic raw signal. Okay. This is a period where they have seen the sand loading. Okay. From here to here, they have seen the sand loading. Okay. And here also some sand loading. This is the acoustic raw signal.
Okay.
The acoustic sand detector has detected some signal. Okay. The sand is loading too much in this period. Okay. Now, if you see the this is a metal loss. This erosion probe metal loss. This orange color.
Okay.
Now, if you see, initially the metal loss is low. Okay. In the event of the sand, the erosion rate increases. And when the sand loading is not there, the erosion is not there. Then after, when the sand loading starts, the erosion starts. Okay. And then there is no sand loading. So there is some flat region. And then again, there is some minimal sand loading. So there is a erosion rate. Okay. You can see that very clearly, that based on the sand loading, the erosion rate increases.
Okay.
Initially, there was some sand loading, so some minimum erosion rate jump, and then it is flat, and then there is a huge sand loading. Then there is a higher jump in the erosion rate because the sand loading is high also, and the duration is also very high. And then there is a minimal sand loading for a shorter duration. Accordingly, the erosion rate jumped to a very small limit, and then it stayed. There is no sand loading after that, so the erosion rate is constant. You can see that?
Yeah.
You can understand this graph?
Yeah.
So, so that's how it is. Similarly, another temperature where the sand loading is there and all. Okay. So, this is all about monitoring, sir. In oil and gas, we use all these type of monitors. And nowadays, we are using one more thing.
So, this is finished or?
No, it is finished. I am trying one more thing. Let me try one more last thing is there. Nowadays, we are using a non-intrusive probe. Okay. I want to show that. That's it. Okay. Allow me to show that.
Yeah.
To share that last one, permasense, what we call, which is the latest technology which we are using. Okay. Permasense we call. So we used this non-intrusive technique. So basically, we have a probe like this. Okay. This is a UT probe basically. We just connect to the outside of the pipes or equipment. Just it will give you, transmit that one, and with the GPS we receive the signal here in the wireless, this one, and this one will transmit the detail into the computer, and then the computer is loaded with software which will interpret the result. Okay. So this is called a permasense. Nowadays we are more using this UT probe. Okay. So it's a UT type probe. There is a data sheet. This is a UT type probe. Okay. Permasense they call.
Okay.
So it will have just a probe. Okay. And then that probe detects the UT signals with respect to thickness loss. And that transmits to the receiver. This will be a transmitter, this will be a receiver, wireless receiver. And then this wireless receiver will transmit that thing to the computer which is connected to that. And then from that we can use the data to get the corrosion rate. Okay. So this is how today we are using this permasense UT wireless probes. Okay. So this is a somewhat latest development. We are using earlier this ER probe, LR probe or corrosion coupon. But nowadays, without entering the system, they are using these UT probes to determine the wall loss and from the wall loss to the corrosion rate.
Okay. So now they are using GPS and that one directly to monitor. Okay.
Yes, sir. Thank you.
Okay. Thank you. Nice presentation.